Next we will discuss the Norton's theorem. Now the Norton's theorem, it is not very different from the Thevenin's theorem. What did you have in Thevenin's theorem? You had a two-terminal linear network, remember the word linear, and this was converted into an equivalent network which is having a voltage source, an ideal voltage source in series with a resistance. Okay. Now how to find this VTH and how to find this RTH value we have discussed in Thevenin's theorem. Now if you remember from source transformation, whenever a voltage source is in series with a resistance, you can convert it into an current source in parallel with a resistor, right? So from here you can get a resistor which is in parallel with a current source. Okay. Now from this form to this form, if you can get, this is nothing but the Norton's equivalent form. So that means if you have A and B terminals, then here there are going to be A and B. Now how to find out this Norton's resistance and how to find out the value of this current source. So that is represented by IN. Okay, N means Norton. If you find out the Thevenin's equivalent, then from here you can source transform and you can directly get the Norton's equivalent, right? So this you can get via source transformation. Okay. Then what about the direct form? That means from this network to this network, equivalent network. So how do you get that? Simply you will have to find out, just like in the Thevenin's case, you have to find out the current IN and you have to find the resistance Rn. Okay. But if you can see from here, whenever you apply source transformation, the resistance value is not going to change, right? So Rn is nothing but the same, the value is same as the Thevenin's resistance. That means in the same procedure you will have to find out the Norton's resistance. Basically they are both one and the same. Okay. Rn is equal to Thevenin's resistance. Okay. Now what about IN? This is the short circuit current flowing through the AB terminals. Okay. So that means if you take the network, this is A and B terminals. Now you short circuit this and you find out the current through this. Okay. So this is how you will find out the Norton's current. So you can, why we are doing that, you can understand from this equivalent. See, if this is the network and you are shorting this, then all of the current will flow through the short circuit, right? So whatever current will flow through the short circuit is equal to the current source. So now we will do a question, find the Norton's equivalent of this circuit. Okay, so the terminals A and B are here. So what do we have to get here? We have to get IN and Rn or RTH, since both are same, and this is the AB terminals. Okay. So how are we going to get, since we already know the method of getting the Thevenin's voltage. Okay. You can get Thevenin's and then from there you can apply source transformation to get Norton's. But here we will do the direct method, that means from the network directly to the Norton's equivalent. So how to do that? First thing is, first you redraw the circuit, the same circuit, and then you can short circuit the terminals. Okay. So here you have a resistor, here there is a resistor and here there is a resistor. Okay. Now these two you are short circuiting and the current through this is IN. Okay. So what are these values? This is 2 ampere, 4 ohm, 12 volt, 8 ohm, 5 ohm and 8 ohm. So you can see that there is a voltage source in series with resistance. This you can apply source transformation. So what are you going to get? Applying source transformation, you are going to get, what will be the value of current here? 12 by 4, which is 3 amperes. This was 2 amperes. And 4 ohm resistor, and everything else will be as it is. This is 8 ohm, 8 ohm and 5 ohm. Now this is the current. Now one thing that you can see here is this short circuit is across this resistor. So this you can remove because no current is going to flow through it. It will be shorted, right? So this you can remove. Now, what will be the current here? IN. You can see that you can simply apply the current division rule here. This equivalent current, how much will both of these deliver? They will deliver 5 ampere, right? Or if it is confusing, you can just add both of them. So how much you will get? 5 amperes. Okay. Now 5 ampere current is being divided into 4 ohms and 8 plus 8. These both are now in series, this and this. Okay. So IN you can find from current division by current division. IN is equal to, since there are only 2 resistors in parallel, you can simply write the other resistor divided by sum of resistors. So 4 plus 16 into 5. Okay. So here you are going to get 1 ampere. So this is the first step, right? So that is finding the Norton's current. Next is finding the Thevenin's or the Norton's resistance. The procedure is going to remain same. There is no difference, right? So the current source, if you have to turn off, you have to replace with an open circuit. Then voltage source with short circuit. So here you have 4 ohms. This is 8 ohms, 5 ohms and 8 ohms. And from here you are going to see the resistance RTH. Okay. So you can see that this is 5 ohms in parallel with this entire resistances, they are in series. Okay. This is in series. So you can write RTH is equal to 5 parallel to 8 plus 4 plus 8. Okay. So you are going to get 5 parallel to 20. So this, if you calculate, you are going to get 4 ohms.